I'm going to think about continuity, semi-continuity. So there was, I produced a guide P183. It was the best part of 25 years ago now, and looked at using semi-continuity. And we can see here what I'm talking about and why it's beneficial. So on the left-hand side, we've got a beam. It's got nominally pinned connections at both ends, and you've got to provide an envelope to resist the sagging moment, and thinking about the deflections that you get there. If you then stick a semi-continuous joint on one end, and by semi-continuous, I'm talking about semi-rigid, so that helps from a deflection point of view, but I'm also thinking about partial strength. And the fact it's partial strength means that you lift one end of that bending moment diagram, and you can see there the benefit that that has on the sagging resistance of the beam that you're going to need. It's quite significant, particularly in a steel environment, which we'll talk about a bit later on. And then if you can get semi-continuity at both ends, then clearly you can get a bigger benefit. And that's thinking about strength. If we think about the serviceability limit state, then this graph I've always found quite interesting with its two asymptotes. So if you have 0 support stiffness, then you're going to get 5/384 under a uniform loading. And if you had a rigid support, then you're going to get 1/384, which is the asymptote down the bottom. And the shape of the graph shows you that you don't actually need a lot of support stiffness to get a significant reduction in beam deflections. And that support stiffness I'll talk about in a minute, because that is not just the joint, but it's the joint, and then it's what that joint is fixed to, which is column above and below, beam coming out the other side, and the joint on the beam coming out the other side. But if you can get a little bit of stiffness, it's probably quite easy to halve the deflection of your beam. So here are some kind of headlines from P183, which was all about semi-continuous braced steel frames. So these are the kind of savings that we were looking at, and it was all using joints that are simple, almost simple in inverted commas. So simple in inverted commas is nominally pinned, whereas simple is just not very complicated. So you're looking at end plate connections. You're not looking at fin plate connections, but you're looking at end plate connections that would often be designed assuming they were nominal pins. Issues with this publication are that it only covers bare steel beams. It doesn't work as written with composite construction. So there are rules of thumb about if you choose such and such a connection with a certain level of partial strength, then you can assume that your deflections will be reduced by a certain amount. Those rules of thumb do not apply if you start adding in the complexity of composite beams. And the other thing that I think is absolutely worth mentioning is that there are standard joints, and the use of those standard joints is essential, because whilst you're going to explicitly consider the moment resistance of this standard joint, you're not going to explicitly consider the stiffness of the joint, and you're not going to explicitly consider the ductility of the joint, in other words, its rotation capacity. By using a standard detail, you know that the stiffness and the ductility will be acceptable and in line with the method, because a range of joints were tested, and so those attributes were quantified. And the fly in the ointment with all this is that those joints, standard joints, are all based on S275 plate. The fact that they're ductile is because the end plates bend. You don't get the bolts breaking or the welds breaking or some kind of a brittle failure mode. Problem there being that you can't buy S275 plate. In fact, I'll rephrase that, and I'm not sure which way round it is, but strip and plate, I think one of them you can get in S275, and the other one you can only get in S355 in the UK, unless it's maybe special order or something like that you wouldn't want to get into. So as a designer, there's a bit of a warning there. Don't come up with a design and specify something using one of these connections if you're only then going to find that actually the fabricator can't get hold of S275 plate, might well not understand the significance, might put an S355 plate on thinking stronger is always better. Well, if you're trying to govern the failure mode, then stronger isn't better in the context of a partial strength joint. So yeah, these are the kind of details we're looking at. I think that the problem, if you've got a composite beam, so we've got semi-rigid behavior, and then we've got a plastic behavior from these partial strength joints. The problem if you've got a composite beam is that a composite beam in sagging is about 3 times stronger than a composite beam in hogging. So if you put a bare steel joint on your beam, it's already going to have significantly less moment resistance than the composite beam in sagging. So you're going to have to get a lot of rotation out of that joint in order to redistribute moment and fully exploit the composite beam. So that's not going to work very efficiently. They need to be partial strength, because if they were only semi-rigid, you wouldn't get that much difference in moment distribution from having a fully rigid joint, which would mean that in hogging, you still had to get quite a lot of rotation to redistribute moment. Yeah, so basically we need the joints to act as a hinge, and we're going to be considering their secant stiffness.